So in fact, when we talk about what causes diffusion to happen, it's a concentration gradient. Like if we're talking about, something changing, there has to be a difference in concentration. Because going back to that movie, what's happening is the atoms are always moving, and just over time, there will be this, it's a probabilistic thing, that's what I was going to say. That there's just going to be an increased probability that they're going to move to areas of lower concentration. So it becomes more and more disordered. Now with solids, in order for this to happen, we've got this, in the solid state, we've got these bonds. So in order for for atoms to diffuse in solids, they've either got to move by vacancies or as interstitial atoms. We'll come back to this. What makes diffusion faster? We already talked about two of them, right? Open crystal structures. And with temperature, as the temperature increases. Okay, so diffusion in solids. We've already talked about like self-diffusion, right? If the vacancies can move, then the atoms have to move. And that makes sense. Vacancies move through the atoms. An individual atom, if we could mark it somehow, would move through. But for this, there's no concentration difference. So we call that self-diffusion. For diffusion in solids, this is what we have. This is what we're familiar with. These are the concentration profiles. So initially, we have a very clear dividing. Pure copper on one side, pure nickel on the other. And over time, some of the copper goes in to the nickel, and some of the nickel goes over the copper. And eventually, we would have like this giant copper-nickel random diffusion of the atoms, or random arrangement of the different atoms. And so eventually, it's going to move to something like this, right? That would be the concentration profile after a long, long time. So how does it happen? We talked about vacancy diffusion. This is for substitutional atoms. And what happens is, if that vacancy is moving through, that empty chair is effectively moving through, that's actually happening because the atoms are moving. And so over time, these random atomic movements result in a net concentration gradient. So now we would have, all red on this side, 0% red on this side. And over time, that happens. So if we have to move that vacancy and form that base, so in order for this to happen, it's going to be faster if there's more vacancies, right? So that's one reason that the temperature increasing would affect, make diffusion faster. What's the other thing? What's actually happening when these atoms move? We're breaking and reforming bonds. So we're constantly breaking up, jumping over this energy hill. So there's an activation energy associated with diffusion, just like there is with vacancies. So for vacancy diffusion, you can think of it as like there's this double whammy. If the temperature is higher, we've got more vacancies, more spots for the atoms to move into, and we've got more energy in the system to jump over this activation energy barrier. Now, if we have an interstitial atom, so it's a small atom, much, much smaller than the host material, it can move in the interstices. And so there's lots of room for it to move that way. So which is going to be faster? Substitutional or interstitial, or vacancy diffusion or interstitial? Interstitial. This is always going to be faster, all else being equal. Okay. So when we talk about diffusion, we're going to introduce this idea of a flux. So a flux is basically how much of something is moving across an area. Okay. So if we have a plane of material, how much is moving across that little barrier there? And how fast is it moving? So you can think of this as like a flow rate or something. It's measured similarly. So we can measure the flux for anything that's moving through the material. We can measure it for vacancies, we can measure it for host atoms or the impurity atoms. But this is the one we're usually concerned with in diffusion. We're looking at impurity atoms. How is that moving through? So let's talk about what you think the units. I'm going to open a few more questions. And let's talk about this. So what do you think the units are for flux? So we said how much material is crossing that area and how fast is it doing it? That's ugly. So 1 and 3. Yes. Kilograms or atoms. Now which one do we could use kilograms or atoms. A lot of the time we try to think about things as more of an atomic percent in diffusion. And so when we went back over concentration of different alloys and calculating that in the structure, you know, when we looked at weight percent and atomic percent of alloys and mixtures of materials, we use those differently. You know, we talk about atomic percent maybe a little bit more for or more so for diffusion, or we talk about flux in terms of atoms a little bit more. Okay, let's put these in order. So that, well, we'll come back to that. Okay, so that's what flux is. How much stuff is moving and how fast. And so flux is effectively the slope here, right? And that's the unit we measure. Slope here on this curve if we're doing mass per unit area versus tone. So when we describe diffusion, one of the important things that we're going to talk about is this concentration profile. Because again, the driving force for diffusion to happen is for there to be a difference in concentration from one spot to another. So we have a concentration difference between A and B. And so because of that, there's a concentration gradient. Now, the important thing here is, which way do the copper atoms want to move? The orange ones, which way do they want to move? This way. So copper wants to move this way, and the nickel wants to move that way. So when we're talking about this concentration gradient, the first thing about diffusion that we need to cover is that it always wants to go basically downhill. Right? The flux of copper is in that direction, right? And the flux of nickel is in the opposite direction for this. So whichever way we've got, and we can draw the concentration gradient either way, right? We could, see we have, so two different y-axes. Sometimes we'll have, just the concentration gradient of 1 shown, like just the orange line, not the gray line as well. Either way works, but the flux is always going to go downhill. So if we're looking at the carbon or copper concentration, the flux of copper is going to go down the concentration gradient for copper. So that's the first thing. Which direction is the flux happening? The second is what's the magnitude, right? So flux has a direction and a magnitude. Okay, so Fick's first law basically says, well, the magnitude of the flux is going to be proportional to how big the driving force is for diffusion. So the magnitude of the flux is going to be proportional to the concentration gradient. What's the other thing that's going to determine, we've talked about how fast something diffuses? Temperature, size, a structure of the atoms, what's diffusing into what? We know that also goes into. So when we've been talking about like diffusivity or how fast something diffuses, that's basically the flux, right? That's where the unit time is. Kilograms per unit area per unit time. So we've been saying that temperature, the species that's being diffused, the structure, what it's diffusing into, all of that can relate to flux, and that's all carried up in this diffusion coefficient. And we'll talk about that more in detail. The first thing with Fick's first law, the other thing that comes in that you maybe haven't talked about before in your classes is the concentration gradient. So if you do a unit analysis, you'll see the units for the concentration gradient are kilograms per meter to the fourth. So the steeper that concentration profile is, the greater the flux. So if we have just a little concentration difference, we're not going to have as many atoms moving over per unit time. If we've got a big concentration gradient, we're going to have a lot more atoms moving over. And how steep that line is speaks to how much does diffusion want to happen. Does that make sense? So that's Fick's first law. Now, so let's go back and talk about some of these diffusion questions. So now we said the diffusion coefficient is basically speaking to flux, right? So if diffusion coefficient goes up, then the flux goes up. So what would be the order here? We've got nitrogen and iron and chromium and iron. So you're going to rank those in terms of from greatest to least, so the fastest and then the slowest. How are they going to rank? So nitrogen first. That's going to be much faster because it's small. It's happening by interstitial diffusion. Definitely faster, greater flux at high temperatures. And then chromium, first at 900 and then at 700 C. Okay. So when we talk about diffusion, we have either steady state or non-steady state. So let's talk about steady state first. What does that mean? What's steady in steady state is the concentration profile. So that concentration versus distance curve that we've been talking about, that's what stays steady. So in order for that to happen, the flux going in needs to equal the flux coming out. If the concentration is going to stay the same, then we've got to have something where the flux coming in, there's atoms coming in, but the same number of atoms are going out. So the concentration in our thing is staying the same, doesn't change. So when we apply Fick's law, we say, okay, so Fick's law is just, we're not going to derive it, this is what it is. So the flux is equal to negative d times dc dx. So we set them equal to each other. Well, we're talking about one atom within, gray atoms and white atoms, so the d is the same in both, right? And we already said the j is the same in both. So effectively, the concentration gradient in here is the same as the concentration gradient over here. Or coming in as the same. So dc dx. dc dx. It's the same on both sides. So what's that mean? If we look at concentration, let's say white atoms, versus distance, what's it going to look like? Well, this is the derivative, right, of whatever line we have there. So what kind of line are we going to have? If it's constant, right, we're going to have a straight line. So it doesn't have to be horizontal. In fact, it's usually not for steady state. But whatever that concentration gradient is, that dc dx, is going to be a straight line for steady state diffusion. So let's consider the steady state diffusion and say, okay, well, say I have a box or a membrane, and I've got A coming in, A atoms coming in to it, and say before this happens, there's no A atoms in my box. But I'm going to tell you that steady state diffusion is going to happen. Is it going to happen right away? Let's see what you guys think. Oh, never mind. Okay. The answer is no. You think about, diffusion is a lot like if you think about something, heat. It's not the same thing. We're not talking about mass transport of atoms. But if I've got boiling water on one side of a really thick, or, better yet, let's talk about a cooler. Okay? So I've got a plastic or a foam cooler, and I've got it full of ice and soda. Eventually, what's going to be true about the diffusion of, or the ice in that cooler? It's going to melt, right? Heat is going to diffuse from the outside in. And eventually, we'll have a steady state in there. But it takes a while for the heat to get to the other side, right? So initially, we'll have a concentration gradient like that. And then it'll get a little bit bigger. And then eventually, we'll have lost some atoms on one side. And then eventually, it might diffuse all the way through. So that's kind of talking about the diffusion couples. The A on one side, the B on the other. That's what we talked about there. For a steady state, we've got, there on one side and nothing on the other. It's going to start like that and even out to a straight line. So that's the progression with time, as time increases. That's what's going to happen as we set up a steady state. Now, when do we get a steady state? Well, this is our initial condition. In order for it to happen, we have to have basically, an unlimited supply of whatever is going into this green box. So an unlimited supply on one thing. And it's the constant. The same supply. So concentration 0 there never changes. That has to be true. And after a while, we'll get this steady state happening. So we have these two constant reservoirs with a constant concentration and usually a very thin boundary between, right? There has to be an in and an out. So we're not talking, so when we talk about thinness, if one of the examples is, that we'll talk about later on for non-steady state diffusion is, say, we're doping silicon with something. We're shooting ions of phosphorus into silicon. So it's the level, the depth that diffusion is happening in is much, much smaller than the actual depth of the silicon wafer. So in order for a steady state to happen, we have to have a thin boundary between them. Now, in general, steady state is not that common. I mean, there's certainly applications where it happens or where it's a very good approximation of what's going on. But non-steady state diffusion is a lot more common. But one example where steady state diffusion does happen is with chemical protective clothing, so basically gloves, okay? So you think of a rubber glove or a nitrile glove or some kind of glove that we're going to wear. So here, on one side, we'll have a certain concentration of, in this example, paint remover. And so on the other side is your skin, and we've got this really thin membrane between them. Well, there's actually a flux of atoms going into the rubber glove and reaching your skin. And because it's a very thin layer, we have a steady state that exists. And so we can calculate the flux of atoms. How many atoms per unit time per unit area? Let's go ahead and do that. So J is negative 110 times 10 to the negative 8 centimeters squared per second. And then dC dx is basically just C1 minus C2 over X2 minus X1. So we can calculate that, right? We can say this is the flux of atoms. So if the membrane is thinner, what's going to happen to the flux? It's going to go up or down? It'll go up. Same thing, obviously, if the concentration difference is bigger, flux is also going to go up. So the lesson here, change your gloves. And make sure you use the right glove. There's actually a story of a young woman who was doing research with mercury and used the wrong gloves. And so got mercury poisoning. So because that diffusion coefficient D depends on what material is diffusing into what. So you want to have something with a really low flux of whatever you're handling. Okay, very quickly, just to introduce the idea of non-steady state diffusion. Now, the concentration as a function of distance is changing with time. So if we're going to conserve matter, then the change in concentration over time has to be the amount of stuff that's left behind. So we still have flux, but they're not the same, right? So the flux on the right minus the flux on the left over the distance is equal to the concentration gradient. So using Fick's first law, you differentiate both sides, and we have this. dj dx equals negative d squared c dx squared. So effectively, this is what we get for Fick's second law. So now, the concentration gradient is changing with time, and how much, or the magnitude, or how much that concentration gradient is changing with time, is related to the second derivative of the concentration with respect to x, so the curvature of the line there. And that's Fick's second law. And so that's going to be, so we have now Fick's first law, which says, okay, the amount of material moving, diffusing through our species across some imaginary area is equal, or is proportional to all the things that go into D that we've been talking about and alluding to about crystal structure and impurities and things like that. So all those things, and also how big the concentration difference is. So we need that concentration gradient. That's the driving force for the diffusion. And so the bigger the concentration gradient, the more flux. Now, the amount that concentration gradient changes with time is related to the curvature of d squared c dx squared, or the curvature of the c versus x profile. And that's Fick's second law. Okay. So on Friday, we're going to go through a lot of problems and talk about, we're going to go through a lot of the math problems and talk about how we use diffusion in material science.